We've talked about hypothesis testing for a population mean, and we've gone through some examples where we drew conclusions about hypotheses with both the critical value approach and the p-value approach. Both approaches give the same ultimate answer regarding whether we reject or fail to reject the null, but they come from different directions. We'll now apply these approaches to hypotheses that deal with population proportions. That is, there's a proportion of successes that exists in the population, and we want to answer a hypothesis about the proportion of successes. Note that much like confidence intervals for population proportions, we assume that the population contains two categories, successes and failures. Remember that successes doesn't always imply a good thing. It's just a way for us to characterize two different categories such that one is a complement of the other. We may ask a question like, is the proportion of defective circuits greater than 0.05? We can collect a sample of circuits, and each of those circuits will fall into one of two categories, defective or not defective. We can then estimate the population proportion with the sample proportion, p hat, and then ultimately compare p hat to the hypothesized proportion, 0.05, with the test statistic. Generally, the notation for the hypothesized value is p naught or p0. We may want to know if the proportion is equal to p naught or if the two are unequal. Or we could have greater than or equal to p naught in the null and less than p naught in the alternative. Or we could have less than or equal to in the null and greater than in the alternative. Much like hypothesis tests for a population mean, the alternative hypothesis gives us an idea of where the rejection region is. Two tails, lower tail, or upper tail. So what does the test statistic look like? Recall from our calculation of the confidence interval that we always use the standard normal distribution for population proportions, assuming that NP and n times 1 minus p are both greater than 4. The test statistic measures how different the point estimate, p hat, is from the hypothesized value, p naught, in terms of standard deviation units. Here we get the standard deviation from the binomial distribution, and we use p naught in its calculation. That is, if the population proportion is indeed p naught, then the standard deviation of the sampling distribution of p hat would be the square root of p naught times 1 minus p naught divided by n. Therefore, the z-naught test statistic is p hat minus p naught divided by the square root of p naught times 1 minus p naught over n. The critical value approach works the same way we saw previously. We state the hypotheses, determine the appropriate distribution, in this case a z distribution. We determine where the rejection region or regions are and what the associated critical values are. We calculate the test statistic z-naught. We compare z-naught to the critical value or values. Then we draw a conclusion relative to the null hypothesis. Same exact idea, except now our hypotheses deal with the population proportion. Let's take a look at an example. At Kruger Industrial Smoothing, ball bearings undergo 4 operations, the last of which is polishing, and then inspection takes place. The inspection process determines whether or not the bearing should be repolished. A polishing machine will be qualified for use if it can be shown to produce less than 8% of bearings that need repolishing. In a random sample of 300 parts, 12 needed repolishing. Based on this sample, can the machine be qualified at 95% confidence? The statement we focus on is less than 8%. Less than implies strictly less than, no equality. We know that the equality statement must be in the null hypothesis. Therefore, less than must be in the alternative. The null hypothesis is p greater than or equal to 0.08, and the alternative hypothesis is p less than 0.08. This is a one-tail test with all of the alpha equals 0.05 in the lower tail. We use a z-table to find the critical value. We want the tail area, but the z-table provides the area between 0 and the value z. So we need to look for 0.5 minus 0.05, which is 0.45 in the table, and look for the z-value associated with this area. The z-value is between 1.64 and 1.65, so let's just say 1.645. Therefore, the critical value that's in the lower tail is negative 1.645. Now let's calculate the test statistic. P hat is 12 repolished bearings divided by 300 total bearings, or 0.04. The test statistic is 0.04 minus 0.08 divided by the square root of 0.08 times 1 minus 0.08 over 300. Z-naught is negative 2.55. We compare this to the critical value. Z-naught of negative 2.55 lies in the rejection region. That is, it lies beyond the critical value of negative 1.645. As such, we reject the null and conclude that the polishing machine produces fewer than 8% of bearings that need repolishing. We draw this conclusion with 95% confidence. We can use this machine in the polishing process. Let's take a look at another example and use the p-value approach. Say you're a usability engineer at Initech, and you are observing the time required to perform a repetitive task measured in seconds. Say that you prefer that the task takes 70 seconds or less. Is the percentage of observations taking 70 or fewer seconds more than 80%? We've got quite a few quantities going on here, so let's focus on the hypotheses. Is the percentage of observations taking 70 or fewer seconds more than 80%? That is the percentage more than 80%? Or is the proportion more than 0.8? This statement refers to strictly more than, no equality. So greater than 0.8 must be in the alternative. Since equality is always in the null, p less than or equal to 0.8 must be the null hypothesis statement. From our sample of 64 observations of the task completion time, we find that 55 observations took 70 seconds or less. Therefore, p hat is 55 divided by 64, or 0.859. The z-statistic is 0.859 minus 0.8 divided by the square root of 0.8 times 1 minus 0.8 divided by 64, or 1.18. With the p-value approach, we find the area in the tail associated with the test statistic directly. Since this is an upper tail test, we find the area above the test statistic. And since this is a one-tailed test, this area is entirely the p-value. If we use the z-table, we find that the area in the tail above 1.18 is 0.119. We didn't specify a particular alpha, but we see the p-value of 0.119 is pretty large. It's larger than most values of alpha that we'd typically consider. Since the p-value is larger than alpha, we fail to reject the null. We can't conclude that the percentage of tasks taking 70 seconds or less is greater than 80%, even though our sample percentage was 85.9. 0.859 and 0.8 just aren't different enough from each other when compared to the variability in sample size for us to conclude that the proportion is greater than 0.8. So we've applied the critical value approach and the p-value approach to examples of hypothesis testing about population proportions. Again, the procedures don't change from one population parameter to the next. The test statistic changes, and maybe the distribution changes, but the overall approach doesn't change at all. Once you get it down the first time, you can keep applying the idea to population means, proportions, and variances.